No, it is 12:35 UTC, so that's 1:20 in London, EST, British Summertime. I was eating broccoli. I started nibbling it off to start counting the branching fractal dimension of it. I always know it's fractal. You can see that if you take a bunch off here, we have this block, and then it breaks down to this division. And then if you take a division off here, yeah, this division, that's the final division. That's 1, 2, 3, 3 branches. So there's 3 scales of complexity. Now, some broccolis are very mathematical in terms of the Fibonacci numbers that make up their proportions. And I was trying to find a nice paper about it, but I can't right now, because it's not a good time to do some research. But just imagine, in terms of the genetics between this species, which is pretty banal, and this Romanesco. I think this species is, well, irregardless of its genre and species, it is the Romanesco broccoli. And if you could map the genetic sequence of both species, understand the algorithms that genetics, not just genetics or epigenetics, but protein networks and the emergent behavior of how the proteins interact. If they have a theory on how they form structure, you can very simply see the difference in the genetic sequence that accounts for that structure and this structure, and just be beautiful to have a theory that would fit prediction at 2 or 3 different scales of complexity between genes. And then we got to go into like networks and chaos theory and turbulence, and that's non-resolvable. In terms of the Hawthorne equations for turbulence, one of the clay mathematic solutions that are not solved in 3 dimensions, because we got to talk about solving turbulence in 3 dimensions to understand the link between genetics and epigenetics to structure and 3D shape. It has to be the case. So it becomes all a little bit complex when you want to think about how these different branches of mathematics and molecular biology link together. Yeah, that's it.